Yeah, so my name is Ryan. I am a member on 8565 TechnicBots. And as mentioned before, we were Team USA last year in Geneva during October. And today I'm going to be presenting on our research project at Geneva, which is called Dioxide Detective. Now, for a little bit of background on what the research project was last year, it's basically trying to help curb carbon emissions and reduce climate change, which is why the challenge itself is called carbon capture. Now, here's a little bit of background on the problems that we're trying to solve with our project. If you take a look at the images on the right, it's really a pretty hellish place to live, right? It's pretty bad. There's flooding, there's forest fires, there's pollution. These are all some significant problems that are happening in our current world, driven by climate change that we need to help solve. Now, what are the steps to mitigate climate change? Well, the first step is accurate carbon reporting. We need to know who's distributing or who's emitting the most carbon and where are they located and how we can help stop those emissions. Things like carbon taxes, carbon incentives that you might hear people talk about all rely on the first part of the chain, which is accurate carbon reporting. But unfortunately, in the United States of America, which is where our team is based, accurate carbon reporting is extremely rare. 50% of emissions are just completely undisclosed by companies. And this is a massive problem because it makes it impossible to even begin the process of fighting climate change. And that is what our project is trying to solve today. So pretty much what our project is aiming to do is produce a low cost yet accurate way of monitoring carbon all across the country and possibly all across the globe. So here's a little bit about the CO2 sensors that we are going to use to measure carbon dioxide. So the reason why carbon reporting cannot be done right now is because carbon dioxide sensors are traditionally extremely expensive and extremely bulky and hard to maintain. You can see that that's the one on the right here. It's bulky, expensive, but it's accurate because current alternatives might be cheap and they might be small, but they're very inaccurate, and this makes them infeasible for the purposes that we want them for, which is actually to make a difference. You can't take some hobby grade CO2 sensor and use it to make such important decisions on a global scale. So what our solution does is it tries to take the best of both worlds, being both cheap and lightweight and accurate. And the other thing we had to consider was when creating our carbon dioxide monitoring system, do we want to use a stationary network of sensors or do we want to use dynamic sensors, aka drones? Well, we consider the pros and cons. So a stationary sensor can 24/7 monitor something. It's attached to the ground, it's attached to the grid. It's able to constantly send carbon data to your dashboard. On the other hand, a dynamic sensor like a drone, it's only able to monitor it for at most a few hours at a time when you send it to a location. However, it can go to pretty much any location within a few hours, and that can be within a few miles, that can be within 100 miles of your deployment zone. So what our solution does is it combines the best of both worlds again, and we use a network of both static stationary drones and dynamic or static stationary sensors and dynamic drone-based sensors in order to monitor both a large area and have constant coverage. So pretty much what our system does, which you'll see in a little bit here, is it takes readings from our stationary sensor network on the ground, and whenever it sees a spike, it sends a drone to investigate further, which is why it's called dioxide detecting. Now, we consulted various experts on this matter to learn more about CO2 sensors, how we can make our CO2 sensors both cheap and accurate, and really how impactful this research can be. So we spoke with Professor David Larry. He is in the UTD, or University of Texas at Dallas Robotics Department, and we spoke with him about how his sensors work. So he's using very high-end academia sensors that cost thousands of dollars, tens of thousands of dollars, and we kind of learned about how accurate those need to be, where they deploy them, and how he's using those sensors to monitor carbon emissions. And based on that, we took inspiration to create our own version of monitoring just on a cheaper scale. We also spoke with Dr. or Mr. Subhajoy Dutta of the United States Environmental Protection Agency, and we spoke with him about really how we can use this carbon dioxide detective to help mitigate climate change, what kind of impacts it might have. And finally, we spoke with Professor Mung of the Southern Methodist University about similar matters. Now, Here is our solution plan. As I mentioned before, we have a network of drones in the sky and sensors on the ground, which are going to be constantly yet effectively monitoring a very wide range of CO2 emissions all across the United States and possibly across the globe. So on the ground, you have the stationary sensor nodes, which are positioned close to major emission sites like factories, like office buildings, and that kind of stuff. And whenever they record a spike, we investigate with drones to get as close as possible to the emission source and create highly accurate reports for carbon emissions. Now, all of this data is sent to the cloud where we have a machine learning model with artificial intelligence that will take all the data that we record and produce an even more accurate CO2 reading. Um, and all that calibrated data is finally fed to a dashboard where we can analyze that data, we can visualize it, and we can present it to individuals. So a little more about our low cost sensor. You can see it there on the far left. It's $60 worth of parts. It contains like temperature readings, pressure readings, CO2 readings, all those kinds of readings regarding the atmospheric details. And then what it does is it feeds all of those different readings into an artificial intelligence uh, machine learning model right there. I'll go more into depth about what kind of model we're using, but pretty much what you need to know is that it takes those inputs, it fuses them, and it determines a final carbon dioxide level output, which is 21 times more accurate than if we just use a normal low cost carbon dioxide sensor. And it is on par with those of the $10,000 sensors that we tested with the help of Professor David Larry. Now, about the dashboard that we're using, right? We're using something called Grafana in order to display our data. It basically creates really aesthetically pleasing graphs. And here you can see it's kind of showing like the different temperature, humidity, air pressure, and CO2 levels collected from various different sensors deployed. And we can use this to kind of see, okay, which companies have the most emissions, do spikes in emissions correspond with certain events, how we can take this data and help mitigate climate change. So as an example, we might notice that at this particular time when there's a lot of commuters, the CO2 level increases a lot. So we can use this data to, take actions and help mitigate climate change. Now, here is the machine learning model that we're actually using. It's using an architecture called long short-term memory, or LSTM. And pretty much what this means is that it's using like a time frame, a window, which is currently 10 timestamps, and it analyzes this window in order to determine the output. So this makes it extremely effective at analyzing time series data, and that's just data that's correlated with time. And that is exactly what we have with our CO2 sensor. If we just had a machine learning model that's taking the immediate inputs from the sensor and trying to determine CO2 levels, it might not be that accurate because we have to consider everything within the context of previous measurements of the entire global time frame, and that's what the LSTM architecture excels at doing, which is why we can see that our improved score in terms of mean squared error or group mean squared error is 25 times better than the original one. And here's a little bit more about the specific layers that we're using in our model architecture. All right, so we didn't just collect data right here in Texas. We actually also partnered with the Indian Environmental Protection Agency, and we were able to collect data from Mumbai, India. And based on this data, we were able to determine that not only in our single location here, but also in a completely different environment, a completely different climate, we have equally accurate and useful results that we can use. And I'll elaborate more on this in the future. Here's all the parts that we're using in this project. We have two main sensors, which are taking our 4 different measurements, and they're all being fed into a SparkFun breadboard, which will read that data and send it to the Raspberry Pi. The Raspberry Pi takes that data, processes it, and then sends it to the cloud, where we have a machine learning model that will determine the final carbon dioxide output and send that to the dashboard. So here's a kind of demonstration of our drone-mounted. So you can see that the sensor is mounted on top of the drone here. That's our $60 sensor. And the readings are being sent real time to our dashboard right here. So we can see spikes in carbon dioxide levels at the exact moment that they occur and investigate. Okay. Okay, so you might be wondering, well, that's all a nice solution, and you claim it's accurate, but how can you trust a high schooler like me? Well, if you don't trust me, how about you trust some industry professionals? At the first Global Challenge, we were privileged enough to speak with dozens of CEOs and CFOs of Fortune 500 companies and various other representatives, including the U.S. Ambassador to Geneva, Sheba Crocker, and Dean Kamen, founder of First and CEO of Data Research. We spoke to them about this sensor and we talked to them about how it can really be applied in their respective industries, right? They're from different parts of the industries. Some of them might manage hotels, some might manage typical STEM research facilities, all these kinds of different parts of the economy. And we spoke to them about how we could actually use this sensor to do things. And they kind of told us about how carbon emission reporting is really so important and is really the first step to helping to mitigate climate change. And they themselves, as the CEOs of these companies, are aware of this problem. And based on this, we know that our solution, when fully expanded, can really help to solve the climate crisis. So yeah, that's pretty much everything about our first global challenge project from last October. Um, I'll take any questions right now if anyone has them. Yes.
About about how much does your Raspberry Pi and other boards, how much does their whole system weigh?
Way. I don't know the exact statistics, but it's probably within like a couple hundred, few hundred grams because the drone is easily able to lift it.
How much does your drone cost?
Oh, so the drone itself can be pretty much anything that you want. Um, It may be a very high quality drone, thousands of dollars. It might be a cheap hobby drone, a couple $100s. It really can be anything that we want. And we also don't need a whole lot of them because one drone is enough to service like a whole 100-mile area radius. So yeah, it's probably the one in the video is probably like around $400.
Always wondered with drones that you need some sort of like permissions to be able to send them anywhere. I don't know. I'm using
Yeah, there are certain regulations which obviously play an important role here. We have to make sure that these drones are not going to be stepping into airspace or anything like that. But obviously, with a full-fledged solution, we will be considering all these things. And in our case here, we are obviously flying within the regulations in our community here in Plano and in Mumbai, India. Yes.
So your sensor, it detects CO2 levels at one position or it has a range?
Yeah, so the CO2 sensors, it's measuring like four different atmospheric conditions, the exact point that it's located, but we have a network of them which covers a wide area. So we might have one space like every mile apart, and we can kind of gauge the CO2 levels in the area, and then if we need more information, then we send in the drone to
How
investigate.
many did you do for your AI model?
How many?
How many sensors did you use to collect data,
So,
train your AI?
oh, the training is done, I believe we use like a $10,000 sensor to as like a baseline to train and like gauge really from like the really accurate atmospheric conditions and then get the accurate CO2 readings. And I believe we use like two or three from the UTD robotics department to do that.
I have a question. What country are you planning on to scan next?
To scan next, I mean, we're not done here in the US, but I think the first plan is to really develop this in the United States. which is the world's second largest carbon emitter, and then move to the next largest carbon emitters like China, like India, and kind of scale accordingly. Yes.
I understand that it's a $400 robot that's running the drone that you have done, but you can scale it up to any amount you want. So what kind of industry that this small drone targets, and what is the industry that big ones are going to target?
So it's kind of dependent on, well, the big drones versus small drones, the main difference is like their range, right? So you might use small drones in an area where you really only expect carbon emissions to be in like a single clustered industrial zone. Maybe in another case, you have emissions that are spread out across a larger radius, so you need a larger drone that's able to cover all those different points in one flight or something like that.
Uh, Smira from online asks, what are some challenges you faced?
So I think one of the main challenges was actually getting the machine learning model to work and actually getting an accurate reporting from that. So initially, we didn't use this LSTM architecture, and as a result, it was not nearly as accurate as we saw. Our readings ended up being 25 times more accurate once we implemented this architecture versus without it. So it was a really big difference to try to get this done, and it took us a lot of research and discussion with professionals to arrive at this solution, which is a lot more effective than without.
Where do you get the data to train the neural network?
So this data is coming from calibrated high quality sensors that we have. And or not that we have, but the ones that the UT robotics department has, those are the $10,000 sensors. But obviously, once you train it on these sensors, and I think they're placed in like various parts of the Dow's Metroplex and whatnot. Once you get the data from these sensors and you train your model, you only need it once, right? And you can distribute it to all your different sensors.
All right, do we have any more questions?
Thank you so much.
All right.